Okay, start rolling right away. We've got a lot of material to cover today. I apologize to you for the big dump, but the idea with today's lecture is to kind of finish the material, finish the first presentation of the material that's going to be presented on the exam on Thursday. So you've got an exam next week on Thursday. After today's lecture, we will have the bulk of the material relevant to that exam covered. And so theoretically, after today's lecture, you should be prepared to go in and finish the homeworks. There's a couple of things we haven't exactly touched on. I'll be filling in the gaps on those in Thursday's lecture. But after today, we should have the bulk of the material covered again. So my idea is that you go home, you start that homework on Wednesday, Thursday, you do it over the weekend, and then hopefully by the time we start next week, you've already got your homework ready, or your homework finished, and you're ready to jump on exam 2. Okay? So one of the things I wanted to mention real quick, last week we basically covered 2 concepts in lab, 2.5. We went into balancing equations, talked about balancing equations. We moved from balancing equations into yields, predicted amounts of chemical that will react if a certain amount of another reactant is used. So I talked most of those lectures. I just wanted to point out that over here on iLearn, under theme 2, so theme 2 is what's relevant to exam 2, there are all of these PowerPoints. Now, I didn't use the PowerPoints when I was talking the lectures, but here they are. This guy starts to introduce the concept of balancing, reviews what a mole is, so you can find that, touches on oxidation and reduction. Here's your PowerPoint for assigning oxidation numbers. You can go reference that. There's some work in assigning oxidation numbers. You can use that for studying if you like. Let's see. This guy here is more work on oxidation numbers, so if you're having difficulty with that subject, you can consult those PowerPoints. What do we have here? This is another PowerPoint presentation on oxidation numbers. And then this one introduces the concept of your batteries. We're going to do this more in depth, but if you want something to refer back to, this set of PowerPoints might help with the batteries. More on batteries over here. This PowerPoint presentation gives help with balancing and converting from grams to moles using molar masses. This is a PowerPoint on solutions, I believe. We're not going to get into that quite yet. Here is where we're at right now. We're going to introduce thermodynamics. So this is a set of PowerPoints relevant to thermodynamics. Go back and review these after we talk about today's, or after we discuss the material that we go through in class today. This set of slides also discusses thermodynamics. So if you have any trouble with anything in lecture, go back, check the slides, see if the slides help. Now over here at the bottom of theme 2 are today's notes. So I'll be working with those on the display above, but you can access them from the PowerPoint. I'll talk a little bit more about what enthalpy is and entropy and thermodynamics tomorrow when I have more time. I'm going to try to get through some problems first today, or really quickly today. A briefing though, a quick briefing. We're going to be looking at that delta H term. I showed you guys in the first couple of weeks that delta G, which is used to predict the spontaneity of a reaction, is equal to delta H minus T delta S. Now we have the delta G, in order for a reaction to be spontaneous, needs to be negative. Delta G is the sum of delta H and T delta S. In today's conversation, we're going to be talking largely about this term. We've got 2 problems that we're going to evaluate and we're going to discuss the nature of delta H for those problems. Some sign conventions. Delta H refers to heat, or energy transferred as heat, when a reaction happens. If delta H is negative, then heat is released by the system. So, if you see a negative delta H term for a reaction, that indicates that when reactants go to products, when the reaction proceeds from reactants to products, there will be less energy stored in the products than was stored in the reactants. One of the ways that we give this to you is in the form of a reaction coordinate diagram, and we'll show where the reactants are at the beginning of the reaction and where the products are at the end of the reaction. If a reaction is exothermic and has a negative delta H, then we have that the reactants are higher in energy than the products, and so energy will be released as you move from reactants to products. So negative delta H means that as you go from reactants to products, energy is released. A positive delta H would correspond to a reaction coordinate where the reactants were lower in energy than the products. And so you would actually increase in energy going from reactants to products. Positive delta H indicates that the reactants have more heat than, positive delta H indicates that the reactants have less heat or less energy stored than the products. As you go from reactants to products, you increase in your energy. All right? Your enthalpy. Now, we're going to take a moment and we're going to break down a few processes. And we're going to look at each individual step in the process and identify where the components of that delta H term come from. So, this first page of today's notes was just my notes, and then I did a record of some tabulated values so that I can go back and do the math. We'll show you how this works. The problem we're going to start with involves a battery constructed of a copper half cell and a zinc half cell. So we've got our two reduction potentials. Take copper, you allow it to gain 2 electrons. The voltage on that is going to be 0.342 volts. Take zinc, you let it gain 2 electrons. The voltage on that is going to be negative 0.762 volts. And the image that we have here is in the zinc half cell. We've got a zinc ion paired with a negative ion in solution. And we've got that solid piece of zinc metal. The solid zinc metal is where those zinc atoms are associated with their electrons, and they're allowed to join the solid phase, and they've got metallic bonding going on there. Over here on the copper side, we've got solid copper metal dipped into a solution of a copper salt, a soluble copper salt, copper nitrate. And then down here, we've got our salt bridge. So by now, and after Thursday's lab, we're supposed to be able to take those half cell potentials and determine the direction of electron flow in this battery. Does anybody want to tell me how we do that? Remind me how we do that? How do you figure out which way electrons are going to flow in this battery? What if I told you that for a spontaneous reaction, delta G had to be negative, and delta G for, I said this in lab and lecture, for these batteries is negative N times Faraday's constant times the cell potential E cell. So for delta G to be negative, for a reaction to be spontaneous, because there's a negative multiplier here, we're going to need a positive E cell, right? So what your job is to take those two half cell potentials and reverse one of them such that when you add the two potentials together, the sum of the potentials is positive. So which of those reduction potentials is going to need to be flipped such that it's positive? The zinc. And so zinc, instead of being written in the term in the direction of reduction, is going to be written in the direction of oxidation, which indicates that zinc will be giving up electrons. So come over here. Let's see, I've got the math done already. You write your two, you flip your zinc reduction potential in the opposite direction. You flip the sign. You add those two numbers together, and now that's your E cell. It's going to be 1.104 volts or something like that once you add everything up. But what that tells us then is that the net reaction will add the two half reactions together to get the net reaction. In this one, it's particularly easy. We don't need to include any stoichiometric coefficients because electrons are balanced. 2 electrons gained by copper, 2 electrons lost by zinc. You add the two half reactions together, and the net reaction tells you that a solid piece of zinc is essentially going to combine, it's going to donate electrons to a copper 2+ ion. You're going to produce aqueous zinc ion and solid phase copper. That's going to be the net prop reaction for this battery. Just an aside real quick here, we could look at that problem from the terms of oxidation numbers, the context of oxidation numbers. In that case, you guys are going to have to do oxidation number problems in your homework and on exams, but in that case, your zinc starts off at 0, yeah? And your copper ion starts off at 2+. Your zinc ends up at 2+, your copper ends up at 0. So we have zinc 0 goes to zinc 2+, and we have copper 2+ goes to copper solid, copper 0, in terms of their oxidation numbers. So it would be safe for this reaction to show, or to say that electrons flow from zinc to copper in that battery. Let's move on here to the next page. So, physically, what's happening in the battery then is the following. Over here on the zinc side, you have what was a solid phase zinc atom associated with its 2 valence electrons bound in the metallic state. It loses its electrons, and that zinc ion pops off into solution and becomes solvated by water molecules. Your 2 electrons migrate all the way over here, where they pull that Cu2+ ion out of solution. That Cu2+ ion was in solution over here, grabs those two electrons, and it joins the solid phase. I've drawn this little checkered perimeter to indicate what is the solid copper metal and what is the boundary of the solution. And so your copper anode is growing in size as atoms deposit onto it. Your zinc anode is actually eroding as the atoms break away. Now, that's created a slight net negative charge in the solution over here. The metal is 0 charge, but the solution now has an excess of negative ions and a deficiency of positive ions. So it becomes negatively charged. That little del minus is to indicate a partial negative charge. And then over here, in this other solution, because you started dumping off zinc 2+ ions into this solution, it becomes slightly positively charged. So we're building up a slight positive charge and a slight negative charge over here. Now what we said about the batteries then was that as that happens, it's going to cause a reverse potential to set up that counters the natural direction of electron flow. Electrons wanted to flow in this battery to the copper, but now as you make this solution more positive, they start to pull the electrons back. And so to counter that, we have down here our salt bridge. And the salt bridge has these multiple ions in it. Once this battery starts operating and these partial potentials establish, your positive ions in that salt bridge will start to move towards the cathode, and your negative ions are going to start to move towards the anode. I've drawn little velocity vectors in there to indicate what direction ions are flowing in that salt bridge. So that acts to counter those potentials. Okay. Now we're gonna introduce to you mechanisms for determining the delta H of a reaction, and the equation that you're going to use is that delta H of the reaction is equal to the sum of H naught of formation times coefficient of the products minus the sum of the H naught of formation of the reactants times their coefficients. You'll see other versions of this statement that you'll be able to refer back to. Let me explain this a little bit. Enthalpy is what we call in thermodynamics a state function. Altitude is a state function. What a state function, the special property that a state function has is that the difference between two values of that state function, we'll call this position 1 and position 2, is independent of the path between those two places. So if you think of not gravity, but if you think of altitude as a state function, if you go from this point to this point, your change in altitude, called delta altitude, is independent of path. You could walk along this line, say this is a hill, and your change in elevation is the same as if you take some meandering path and end up at the same place. So we call this path independence. Functionally, what that means for us is that in order to calculate the differences in enthalpy between two positions in a reaction, all that we need to know are the initial point and the end point. We don't need to know the path because the path is independent. And so if we can define what is the amount of enthalpy in the products and what the amount of enthalpy is in the reactants, we simply subtract the enthalpy of the products from the enthalpy of the reactants, and that gives us the net change in enthalpy for the process. We're going to use this in just a second. Do this two ways. Look at our net reaction here. So remember, for this battery, the net reaction was that copper 2+ in the aqueous state plus zinc solid forms copper solid and zinc 2+ ion. If we want to do a delta H calculation, the delta H is going to be, again, the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. There's little n's there for the stoichiometric coefficients, if applicable. I've written the equation up here, and just above, I've given numbers for the delta H naught of formation for a compound. This 64.77 applies to the solvated copper 2+ species. And so the amount of enthalpy that copper 2+ has when it's in aqueous solution is 64.77 kilojoules per mole. Your zinc has, in the solid phase, 0 enthalpy. So the net system, copper and zinc put together, if you got copper ion and zinc ion together, your total amount of enthalpy held is 64.77 kilojoules per mole. Over here in the copper, right down below here, or right up here, I've written the copper enthalpy of formation at 0, solid copper. And up here I've got the zinc ion enthalpy of formation, it's negative 153.89. So what we're going to do is we're going to take the sum of the products, copper and zinc ion, we're going to add those two together, and we're going to subtract from it the sum of the reactant enthalpies, 64.770. We then subtract the enthalpy of the reactants from the enthalpy of the products, and we get a number for delta H of the reaction, which in this case is 218.66 joules per mole. What that means is that when this reaction proceeds and solid copper is formed from a solution of copper ion and zinc metal, zinc ion is formed, negative 218.66, that should be kilojoules, not joules. Negative 218.66 kilojoules of energy are released per mole of that reaction proceeding. Let's take this a little bit further. Let's talk about what this number means. 218.66 kilojoules of heat is released in this process. Let's see how that breaks down. I told you guys in the lecture and in lab for a minute that the energy changes, the net energy changes over the course of this reaction was the sum of several different individual steps. We're going to look at each one of those steps. We're going to break this reaction apart into each individual step. We're going to create right now a path that leads us from the reactants to the products after we review this real quick. You can think of the removal of an atom, or the addition of a gas phase atom to a solid, as being an energy releasing action. So if you've got a solid piece of metal, then you want to take one of those atoms, and its electrons in this case, and remove it from the solid, you're going to have to spend energy. The reason for that is that there's low potential energies in the solid state. Metallic bonding is a situation where protons and electrons have come together in such a way to lower their total energy level. Electrical potentials are lowered, there's changes in the kinetic energies of the electrons, but suffice to say, there's a low energy state that you achieve when you are associated with other solid phase species. And so copper, taking a single atom of copper from the gas phase and transferring it to the solid phase, releases, I got two different values from two different sources, but it's 337 to 338 kilojoules per mole of heat. And so largely, that is the electrical potentials lowering. And when those electrical potentials lower, energy is released. 337.4 kilojoules of energy released per mole of copper atoms moving into the solid state. Over here, you look at the same energy for a zinc atom. A zinc atom doesn't release as much as copper, but it still releases energy. A zinc atom going from the gas phase into the solid phase, you're going to lower that, you're going to release 130.5 kilojoules of heat. So the zinc atom has kind of tight binding to the solid phase. Right? From this comparison, we can tell that the copper atom has tighter binding than the zinc atom, yeah, because more energy is released by the copper atom. Pay attention to that, that's important. So we've got the differences in energy between the solid state atoms and the gas phase atoms. Another thing that we have to look at are the ionization enthalpies. So there's a certain amount of heat transfer, energy transfer in the form of heat, that happens when electrons are added to or removed from a nucleus. copper, if we wanted to take a solid gas phase copper atom and pull its electrons off, it's going to cost us energy, right? Those electrons are bound to the copper by their electric potentials. And to remove them, we've got to exert forces. 270 or 2,703.4 kilojoules per mole of copper atoms ionized. Yeah? Over here, we look at the same thing with zinc. It costs you energy to ionize a zinc. You want to pull those 2 electrons off of the zinc, it's going to cost you 2,639 kilojoules per mole of electrons removed from zinc. Now notice, while these 2 numbers are comparable in size, copper binds its electrons just slightly more tightly than zinc. The copper ion, it takes more energy to remove electrons from copper than does zinc, and so then copper, therefore, is holding on to its electrons more tightly than zinc. All right? One more point. If we just got to the point where we had a gas phase copper atom, sort of. We looked at the energy to move copper atom into the gas phase. We also looked at the energy to ionize that copper atom once it was in the gas phase, or zinc atom once they were in the gas phase. Now, we're asking ourselves the question about how much energy is absorbed or released when we take a gas phase ion and we put it into aqueous solution. Well, we've said a million times that ions in aqueous solution get solvated by water. Water aligns its dipoles with the ions in such a way as to bring positive charge close to negative charge to lower the electron potentials. And so it won't surprise you to see that these processes have negative delta H's, indicating that when you solvate an ion, you go to lower energy value, therefore releasing energy into the surroundings, releasing heat energy. Your copper, if you take copper 2+ and you move it from the gas phase into the solid phase, negative 2,289 kilojoules per mole of energy are released. 2,000 kilojoules, 2,289 kilojoules of energy released when those water dipoles solvate that copper ion solution. Same thing happens with zinc. 2,247 kilojoules per mole of zinc that goes into solution. So note then that both copper and zinc are bound by the solution. It turns out that copper is bound just slightly more tightly than zinc is. Yeah? And so we have that. Now we're going to get into the point, or to the place where we start to use, where we start to sum this all together. First of all, I want to say that I've taken 6 different individual processes and kind of put them together. We're about to look at the total sums of the energies. But a real quick point that I want to make is that these processes provide a path between the reactants and the product. So the reactants in this, we had Cu2+ ion and zinc solid. In the products, we have Cu solid and zinc 2+. The calculation that we did when we first looked at this problem corresponds to a direct path between the products and the reactants. We're about to execute a calculation that moves along a path that stops at a couple of different places on the way, but has the same beginning point and the same end point as the direct path. So we executed a calculation for delta H along the direct path. We're now going to execute a calculation for delta H along this kind of segmented path. But what we should find is that delta H's are the same, because initial and the final states.